Engineering application. The second law of thermodynamics is presented as it was developed, with some additional comments and in a modern context. The main implication is the limits it imposes on processes. Some processes will not occur, but others will, with a constant on the operation compute cycles such as heat engine or heat pumps. Nearly all energy conversion processes that generate work, typically converted from mathematical to electrical work, involve some type of cyclic heat engine. These include the engine in a car, a turbine in a power plant, or a windmill. The source of energy can be a storage reservoir, fossil fuels that can burn, such as gasoline or natural gas, or more temporary form, for example, the wind kinetic energy that ultimately is driven by heat pumped from the sun. Machines that violate the energy operated that generate energy from nothing are called perpetual motion machine of the first kind. Machine that violate the energy equation. Say generate energy from nothing. Are called perpetual motion machine of the first kind. Such machines have been demonstrated and investors asked to put money into their development, but most of them had some kind of energy input not easily observed. Recent examples are cold fusion and electrical phase imbalance. This can be measured only by the knowledge in engineering. Today it is recognized these processes are impossible. Cold fusion or electrical phase imbalance. Electrical phase in These can be measured only by knowledgeable engineers. Today it is recognized that these processes are impossible. Machines that violate the second law but obey the energy equation are perpetual motion machine of the second kind. Machines that violate the energy equation say generate energy from nothing, but obey the energy equation are called perpetual motion machine. Of the second kind. These are a little more subtle to analyze, and for the unknowledgeable person, they often look as if they should work. There are many examples of this, and they are even proposed today, often hidden by a variety of complicated processes that obscure the overall process. This picture shows the process limited by the energy equation first law, and the first show the bar that violate the first law. It is possible, but in the opposite direction impossible without any forces. Punching ball, also some as an relay example for the processes limited by the energy equation first law, energy conversion, and also the heat engine process. And this picture shows the process limited by the second law. Heat transfer, no work, flow, no kinetic energy, and potential energy conversion, also energy conversion as possible and impossible parts. And chemical reaction like combustion, fuel air products, fuel air impossible, heat engine mixing, hot and cold warm, and warm to hot and cold impossible, mixing, and the opposite process is impossible. Actual heat engine and actual pump also another application for the actual heat engine. And heat pump. The necessary heat transfer in many of these systems typically takes place in dual fluid heat exchanger, where the working substance receives or rejects heat. These heat engines typically have external combustion of fuel, as in coal, oil, or natural gas-fired power plant, or they receive heat from a nuclear reactor or some other source. There are only a few types of movable engines with external combustion, notably a Stirling engine, we'll discuss it later, that uses a light gas as a working substance. Heat pump or refrigerator all have heat transfer external to the working substance with work input that is electrical, as in the standard household refrigerator. So heat engines external fuel, external combustion of fuel, as in a coal, oil or natural gas, receive heat or from a nuclear plant, and for the refrigerator or heat pump, heat pump or refrigerators all have heat transfer external to the working substance with work input. Have heat transfer external to the working substance with work input that is electrical. As is the standard house refrigerator, but it can also be shaft work from a belt, as in a car air conditioner system. The heat transfer requires a temperature difference, and we have this relation if you Q dot H CH delta TH and Q dot L CL delta TL, where the C's depends on the detail of heat transfer and interface area. That is, for a heat engine, the working substance goes through a cycle that has the temperature for heat engine, T high, TH minus delta TH, and T low plus delta TL. So the operating range that determines the cycle efficiency becomes delta TH P equals to T high minus T low TH minus TL delta TL. This effect is illustrated in the picture in the next page. For both the heat engines and the heat pumps, notice that in both cases the effect of the final temperature difference due to the heat transfer is to decrease the performance. The heat engine's maximum possible efficiency is lower due to the lower T high and higher T low as shown in the picture. The heat pump's COP is lower due to the higher temperature. For heat engine with an energy conversion process in the working substance, such as combustion, there is no heat transfer to or from an external energy reservoir. These are typically engines that move and thus cannot have large pieces of equipment as volume and mass and undesirable as in car and truck engine, gas turbine and jet engine. Let the working substance become hot, it has a heat transfer loss to its surrounding that lowers the pressure and thus decreases the ability to do work on any moving body. These processes are more difficult to analyze and requires extensive knowledge to predict any net effect like efficiency, so in later chapters we will use some simple models to describe these cycles. A final comment about heat engines and heat pump is that there are no practical examples of these that run in a Carnot cycle. All the cycle devices operate in a slightly different cycle determined by the behavior of physical arrangement. Some historical development in thermodynamics say that progress in understanding the physical science led to the basic development of the second law of thermodynamics before the first law. A wide variety of people with different backgrounds did work in this area, Carnot and Kelvin among others, that combined with developing in mathematics and physics helped foster an industrial revolution. Much of this work took place in the second half of the 18th century, followed by applications continuing into the early 20th century, such as steam turbines, gasoline and diesel engines, and modern refrigerators. All of these inventions and developments had a profound effect on our society.